Hello, everyone.
Morning.
Sorry for the somewhat late start. I'm gonna ask that if you have questions, say about the assignment, that we wait until after the lecture, for those people that came for the lecture specifically. Also, because this lecture is actually going to have a rather separate topic, so you should be able to understand that without having those questions answered yet. So let's leave questions for the assignment to a little later and get on with this here lecture. Yeah. Okay, so today we're going to look at a numerical application that is fairly common in scientific computing, and specifically how to do that in our advertised way of not coding yourself. So we're going to look at fitting, and we're going to look at Fourier transforms. And those two actually are kind of related. So that's why we can do them sort of in one lecture. So fitting and Fourier transforms. So we look at fitting first. So what's fitting? Well, it's fairly common to have data in science, and it's not uncommon to have a theoretical curve or function that you think this data should follow, but it has some parameters that you want to know. So that is fitting the data to a theoretical function and finding those parameters. And in fact, a lot of the field of machine learning is some form of fitting, where you have data, you have a model that you think the data should follow, but there's parameters, and by finding those parameters, now you can learn about that model, and that model can then be used to predict new points. So we're going to look at a much more simpler case than most machine learning, so that's why we really just call it fitting, and how to do that numerically. So this simple case is going to be data that is supposed to follow a linear relation between two variables, and we'll call them x and y. And so the first thing is to get some data. So fitting is fitting data. Where does the data come from? So we're going to just generate some data so that we actually know for sure that it comes from this linear model. And so we could easily see if our fitting routine is any good. So this is going to be a linear relation between two sets of data. The first set of data is a set of x values, and the second set is a set of y values. And the main point of where this gets computed is in the bottom here, where from the point xi, we compute the point yi by multiplying by a and adding b. And in addition, there's a bit of noise. So the noise is random, and that's where a lot of the extra stuff comes in. So I've made this as a module. There's a single function in this LM data module, so it creates data from a linear model. And so this is the header file, but it just repeats the declaration of the definition of the function here. And this function, it's worth has a few nice C++ features. It returns x and y. Both of them are R vectors of doubles. So the first R vector is essentially a set of x values from x min to x max, n points in total. So I'm using the linspace function from RArray in here to compute that. And then y is computed from that in the loop. The randomness, we'll have a whole lecture about randomness a little later on, is done using the random library that comes with C++. So that's nice. We don't have to have a separate library, and you'll just have to trust me at this point that by defining these particular objects here, RNG and Gaussian, that plus Gaussian RNG will give me an extra normally distributed random number with a standard deviation of sigma. So that's quite a few parameters. So they're all put into this function. So the number of points I want, the range of x values, the a and b that govern the linear relation, the sigma, so the standard deviation, and then a random seed that basically kickstarts the random numbers, and we'll as I said, we'll discuss that in greater length in the next lecture. So those are things that come out. What comes out is two arrays, x and y, or two vectors really, and I want to pair them up and just return them as one thing, and we can do that using an STD pair, which is also standard in C++, and it actually is defined in the utility header. That's why utility is here. So utility gives us the pair, which we can now return. Our array gives us the lin space, and that's how it works. So to use this in a function, so this is our LM data module. We include the LM data header. We're going to write to a file, and we're going to use GSL to fit things. So I just added those header files here, but they're not used yet. And then I define my parameters. I always like to give you my parameters names, even if they are sort of hard-coded here as values. Still, I can sort of see what each of them means by their name, and that is a good programming practice. And then here I'm going to create another one of these pairs. So it's a pair of a vector and a vector to hold the result of the LM data function. So LM data is called as a function. It's assigned to XM pair. This now contains those two things, but it gets a little annoying to have to write xy pair dot first to get the x values and dot seconds to get the y values. So I'm actually sort of petering out those arrays again by defining an actual x R vector and y R vector that is just whatever is in the first or whatever is in the second. So this is only creating the data. It's not doing anything yet. It has a little comment there that says I will do something, but I will always like to check that things are already compiling. So I compile things, and then I have my linking line already. Keeping in mind I'm going to use the GSL for fitting, and so I've got my GSL libraries here, and I run it, and nothing happens because nothing is supposed to happen. This is all internal in memory, and nothing really is left. But this is just generating some data using a function LM data. And we're going to use this a few times, and so that's why it's nice to have it just wrapped up in a function. Does this kind of make sense? Let me know if there's questions. Okay. So, yeah, go ahead.
No, it's all good.
Okay, good. Thanks. Okay, so now we want to do a fitting. So this is a linear set of, this is data. Now we just have data, right? We have our x values and y values. We think that it's a linear relation. We of course know it because we generated it ourselves, but assume that this is data we got from somewhere else, and we think it's linear. Now we want to fit it to a linear line, so a straight line model, using the GSL. So GSL has a bunch of stuff in it, and regression, another word for curve fitting, is in there too. So linear regression is done in GSL fit linear. How do I know that? I just go to the GSL documentation, or I just Google GSL and then linear fit, and this will pop up. And so it is a function that, not unlike our LM data function, has a lot of parameters. And because this is C++, or it's really C, there'll be pointers in here. There will be how to say that, lots of everything that I want to pass in has to be passed in explicitly, and so I will have to read the documentation to know what they all mean. And it is important because a lot of these are just const double stars, but their order matters, right? So I can't put an x where it expects a y or vice versa. They have to be in the right order. So there's no way around it. We have to read the documentation, and it says, well, pass in an x, pass in an x stride. We saw this in the BLAST routines as well in linear algebra. So you could have an array that is, say, 100 data points, but you only want to use every 10th, then your stride could be 10. We're usually just using a stride of 1, so we use all the points, but you could do that. Similarly for y, so y is going to be a pointer to the first element. This is a C library, so it likes pointers to the first element. It doesn't understand arrays or R arrays or any other C++ things. Vectors doesn't understand those. We have to give the pointer. Because we have to give the pointer, we have to give the size of these two. So that's n. And then things are going to come out. So the rest is actually outputs. The coefficients C0 and C1 are in the linear relation. And then it also gives you the covariant matrix back, as well as the sum of squares And we'll look in a little bit later what that exactly means. We are right now just interested in the C0 and C1, but we have to create variables to capture these other things and store them somewhere, even if we don't use them. So let's use that. So the first part of this code here until the comment fit xy is what we saw in the previous slide. So that just generates our x and y values, which are just vectors. So xi and xy. So xi and yi are a pair of data. And we create some variables to receive the result from GSL fit linear. So I'm giving them the same names as here, just to make it simple. And I'm going to pass things in now. As I said, this is a C library. It wants pointer to the first element. X and Y are arrays. So the pointer to the first element is just x.data. Our stride is 1. We want every element. We don't want to skip elements. Here's the Y data. The size of the data set is just x.size. I know n here too. I could have used that too, but this is just in case I forgot that there's an n over there. And then the rest has to be given as pointers too, because it has to fill them. And it's a C library, and C libraries doesn't know pass by reference, so we have to give it a pointer. So I have to ampersand each of these elements to make them into the pointer to them, so that this function can actually fill them. So I've called this, and then that's it. The fitting is now done in some sort of magical way. And I can print out what the A value is, which would be C1, and what the B value is, which would be C0. And then to check this, I could also just estimate some points. The GSL actually has a GSL fit linear estimate function in it, which essentially just computes this relation, but it also computes error estimates. So it's kind of nice. You get more than just the point Y out here. You also get an error. And so we're going to compute those for all of the x values that we have, and we're going to print them out just to a file called fit.dat. Oh, other way. So to compile this, we don't have to recompile lmdata. So this first line is actually not really necessary. We already have lmdata.o, but now we compile fit with GSL again to an object file. We link them together. Now it becomes important to have the GSL and the GSL CBLAS in here. And then if we run it, we get the values of A and B that are given here. They are kind of close to the values, so 2.5 and is what we really used to generate the data. We get 2.32 out. B should be 1, but it's 1.622. But you have to remember, we only took 10 points here. So these are 10 samples. You can't expect too big an accuracy with such a small sample size. So so essentially this is done correctly. Any questions? So this is very GSL-ish, right? We don't know how it does it, but we read the documentation, see what it passes in. We make sure they are pointers when it wants pointers, and then we use the GSL routines again to compute predictions. This is not the only kind of regression that's in the GSL, so linear isn't the only kind of fit you can do, and then there will be appropriate estimate functions for that too, but this is the simplest case. I've plotted the result just to see what that graph would look like. I usually do my plotting either in Python or in GNU-plot. Not using any C++ for that because it's too tricky to do that for the purpose of just generating a plot. And the linear line is the prediction. Sorry, is the fit, whereas the data is here. The fit comes with an estimate of an error, right? So these error bars are on the fit. That might seem a little bit silly because usually you see the other way around. Data has error bars and then your fit does not. But because there is an error or an estimated error in the parameters A and B, this can be translated in an error estimate for each prediction. Right? So it gives the uncertainty nonetheless. Okay, so what has GSL really done? What has the GNU Scientific Library really done here? So we started with some data, X and Y pairs. We assume that there's a linear relationship between X and Y, right? So we don't know anything about how it was generated. GSL definitely doesn't know it. But because we're using GSL_linear fit, we assume a linear relationship. And that means there's two parameters, call them A and B here. GSL called them C0 and C1. And so we're assuming that that's the case, but we're allowing for some noise. What we want is estimates of A and B. So we want to know this linear relationship better. We want to know an estimate for these functions, these parameters. If we have those, we could actually predict other y values. So if a specific set of x values, with the estimates for A and B, we could predict new y values for any other x values. And so this is where it will suddenly be called machine learning, because the machine has learned how to predict y from x. I'm slightly short selling the field of machine learning here, but it's so often oversold that I think that's okay. But that's the idea here too, right? This is a form of machine learning, albeit a very old and somewhat simple one. So what is really done is it's assumed that epsilon here, this extra random thing, is a normally distributed noise with some variance that doesn't depend on x. So we don't have to know what the variance is, but you have to know that it doesn't depend on x, which is an assumption. And then you can use what's called the residuals. So you could make a guess for A and B. You could compute what your prediction would be, what the function f would be for those given A and B's at every point xi that you have, and you could see how close that is to the actual value. And then you could square that, and it's supposed to sum it over I. So sum it over all of the points, and that gives you the residuals for any given A and B. And then what you will do is you will try and minimize that residual. That by doing that, what you're actually doing is not so much finding the most probable A and B. It's more like you have a set of data. If you have a given A and B, how likely would that data be? And that's kind of what this measures. So what we're doing is we're maximizing the likelihood of the data given A and B, and then we want the most likely data. So the way you find that is to minimize this quantity. So you want those values of A and B, those values A star, B star, those are specific values, such that those are the ones that minimize this RSS function. So this is called ordinary least squares. So you can see where these squares come from. These are all squares. You want them to be as little as possible. But what is nice is because this is a linear function in A and B, you can actually solve for this minimum without doing actual minimization routines, but by just doing some linear algebra. So this is what's done to find A and B. What's nice about this approach is that you can generalize this. You could have actual error estimates in Y and take them into account in this procedure, or error estimates in X. So your data could have known error estimates. You can use actually any model that is linear in the parameters. It doesn't have to be linear in the X values, in the independent variable. But it as long as it's linear in the parameters, the whole thing still works. You should be careful though. So that means that you can also plot or fit to a quadratic function or a cubic function. So any polynomial. It's very easy to get very good fits by having a large degree of a polynomial. But in those cases, often those fits don't mean anything. What you're just fitting is the noise. So suppose we added some x squared here and so x to the third. We would probably be fitting the random noise more than actually the relation that is there. So it's easy to overfit. You should be careful with that. You can also have nonlinear parameters, but then you have to solve your least square. So that is a bit more complicated. You don't need to use necessarily this RSS thing to minimize that one. You could have other what are called cost functions. This function here, RSS, is actually very susceptible to, or very, very sensitive to outliers. So if you have a measurement error and one of the y values is really, really large, it tends to dominate and it tries to fit that outlier. And so you'd have to do some data cleaning yourself and convince yourself that you should probably throw this away. Whereas other cost values might just not be so sensitive to that. So we're sticking with this linear stuff here for now as an example, but there's many other ways to do this. Okay, so the GSL solves this, but it is nice to look at exactly how it solves this, because it will give us actually a connection between this least square fitting algorithm of the GSL and the linear algebra stuff that we saw in the previous lecture or 2 lectures back. So we're going to go through a little bit of math to show why there is this connection between least squares fitting and linear algebra. And that will hopefully also make it a little clear why whenever we compile something with the GSL, we don't just have -L GSL, we also have -L GSL C blast. So why do we need that blast stuff? It's because GSL actually uses linear algebra in its routines. Let's look at a general model. So a general function f that we're trying to fit to, which is a sum of terms. And so there's b terms here. Each term is some sort of function of x multiplied by a parameter. So it's linear in these parameters beta j. And I assume that the number of parameters here is denoted by b. So to make the connection with our linear case, we had two two terms, a constant and a linear term. So the first one would have been a constant term, f1 would be 1. The second term would have been x, and then the prefactors happen to be sort of reversed. So beta 1 turns out to be the b, and beta 2 would be a. So that is how we would get back our linear model. But this is a more general form where we could have some of the f's being a polynomial or an exponential function. You could have pretty much anything here. Okay, so that's our function. And now we have, say, n data points, so n pairs of xi and yi. What do we need to minimize? So here's this RSS function again. So our yi is the measured data, and this is the prediction, right? So it's just taking f of x, but I substitute that and put in the xi value that corresponds to the yi. So this gives me, for a given set of beta j's, a residual, and now I want to minimize that. So I'm going to write that a little bit differently. There's a matrix here hidden because I have fj xi, and I'm going to view that as a matrix with components capital F j I. So for every j and I have a number, and so that makes it a matrix. So the rows are given by the j, which is the number of parameters, and the columns will be the data points. Okay, so this is a matrix F with b rows, so b being the number of parameters, and n columns, where n is the number of data points. If I do that, and if I try to minimize this just by taking the derivative with respect to the parameters beta and setting that to 0, that can actually be solved, or what I have to solve there turns out to be of this form. So I can rewrite whatever comes out by taking the derivatives in a matrix form. So F is now a matrix. Y is the vector that is composed of all of the y values of the data. So it's y1, y2, y3, etc. until yn. That's that vector. And I act on that vector with F. So this is a matrix vector multiply, which will give me a new vector of b elements. So this is b times n, y is n, so this is a vector b. And then on the left-hand side, I have my elements beta as a vector, so that is beta 1, beta 2, beta 3, etc. And then I have a matrix acting on that, actually two of them, so F times F transpose. So if to transpose a matrix, then multiply it on the left with itself. And that also is a b by b matrix once I've done F times Ft, right? You could, if you like, and if you like a bit of algebra, you should check this yourself, but this is what comes out. When I take the derivative, I set them to 0, it's equivalent to this set of equations. And that's so just to, because it's not so clear, the x values are still in the F, right? So F contains all of the x values, and the y values are in this y vector. So both x and y are still in there, and by solving this equation, I will get the vector of beta, which is all the parameters. Now that's just a linear set of equations that I have to solve here. It's basically ax equals b, where b is right-hand side. This is our matrix A, and x in that case, this is our vector of data. So we have to solve for beta, but that's just linear algebra. And we have solvers in LAPACK or LAPACK-E to do that for us. So we're not going to do that ourselves. We have ways to do that, even if in this case, it is actually a 2x2 matrix and a two-element vector. And so we could pretty much do this by hand. But anyway, that's in the general case, if you had more parameters, you wouldn't want to do that by hand. You would use LAPACK-E. So let's do it. Let's see how that would go. We've seen how to do linear algebra, how to call BLAST routines and LAPACK routines. And so we're going to just do this. So we start off, the first few lines here are the same generation of an X and a Y pair. So if there's an X vector and a Y vector with the exact same parameter, so they will have the exact same values. And now I'm going to fit this to the linear model using the linear algebra I just described. So there's two terms. So n terms is our capital B parameter here, but I don't like short names for parameters in my code. I like them in my math, but not in my code. So this is n terms. And n is the number of points. So here's our F matrix. As promised, it's B times n. So n terms, rows, and n columns. There's a matrix FFT, which is going to be a very funny abbreviation in a second, because we will use FFT as Fourier transforms. But FFT is meant to be the matrix F times the matrix F transpose. So we just get that ready. And there's going to be another vector, which is F times Y. So the result of F acting on Y is going to be a new vector, and that's going to be called Fy. It turns out that we're going to need an integer array of n terms for pivoting in the LAPACK solver routine. I'm just getting that array ready here. We don't really need to know why that is the case at this stage, but it is important to be available for the solver in LAPACK. So we just give it that. Then we initialize our matrix. So we have n columns, remember, and we have 2 rows in this case. So the 2 rows are 0 and 1 are done explicitly. This is the value of the first term, which is the constant term for every value I. So that's just always 1, whereas the second term is x, xi in this case. And so this fills this matrix with exactly the values at once. And now I have to do a few things. I have to compute F times F transpose. So I'm going to use the dgem routine for that. That's the general matrix multiply of double precision. And so and what is nice about the dgem is that you can actually hold on a second. Sorry about that. What is nice about the dgem is that you can have you can specify that one of the matrices is actually supposed to be transposed. So I have the C-BLAST node transpose for the first matrix and a C-BLAST trans for the second matrix, which means I'm multiplying a matrix times a transpose of the matrix. All the matrices are n terms by n term, or the result is n terms by n terms. The intermediate dimension is n, and then there's some extra numbers that come from the general form of the multiply that allows for prefactors. So we just set them to 1 and 0 respectively. We have to pass pointers to C-BLAST. So here's our F data. Here's the size of the one of the sizes of that matrix. Another F data, because we're doing the same matrix, but this F data is interpreted transposedly, if that's a word. Again, with n elements on one of the rows. And then we want to return the stuff into FFT. So I'm giving the pointer to the FFT data, and that itself has a leading dimension of n terms. So that's a matrix multiply that does FFT. There's a matrix vector multiply here too that does F times Y. So it's very similar, except we have Y data here, and the rest, and I'm putting it into Fy. Okay. I'm going to create a copy of the Fy, because it turns out that the solver routine DGESV overrides my Fy. So if I wanted to use Fy again, we lost. So I create a copy of that for the results, and I call the solver. So it's doing a simple solve. and then the returns are in the result coefficients, and so that's A and B, and this reversal of 1 and 0 is what you saw in the example already. So if you run it, you have to compile the fit layback, that's what this one's called, link them together. In this case, you have to link it with a BLAS and layback implementation. OpenBLAS has both BLAS and layback, and so that's an easy one to link into. And then if you run it, we get the exact same values of A and B. So it kind of shows that with more code, we can get the same thing as with less code. But what is actually happening in the GSL is it does things like that. It calls BLAS routines to do these things for it. And that's kind of why when we linked in the BLAS part, where's BLAS, we had to give it a GSLC BLAS because these things are actually using BLAS routines behind the scenes. Okay. So that kind of ties the linear algebra to the least squares and to the GSL. But obviously, in this case, I would definitely prefer the GSL version because it's much shorter code and it does the same thing anyway. Okay, so suppose that we have some data, maybe it's a time series, and it's kind of noisy. So we want to get rid of the noise, which is another way to say that is we want to get rid of the high frequencies in the signal. Then you might think of fitting to a periodic function. So here's a periodic function, and I might select the frequencies that I do like and try to fit my result to it and get the new signal by just throwing away the noise. That's nice. It's linear in these betas, so we could do least squares for this, just as we did. But because these are oscillatory functions and I'm throwing things away, what you tend to get is a very oscillatory behavior of the data, and it's not a very nice way to do it. In fact, it's a kind of expensive way to do it. So there's a better way to do essentially frequency analysis of time signals or a wave vector analysis of waves, and then using these squares for that. And that actually goes by Fourier transforms. So Fourier transforms could be seen, you can see it in a few different ways. So let's just go to the more general form of the Fourier transform here. So what are Fourier transforms again? So suppose we have a function f of some variable x. Here it is. Here's one function. This happens to be the function e to the minus absolute value of x. X is plotted here. This is the function f. Nice cusp. I can Fourier transform this, if I want, to a function by integrating the function, but multiplying every value by a complex number e to the ikx. Whether it's plus or minus, it's up to convention, doesn't really matter as long as you stick to one. And that gives you a new function depending on k. So x is integrated from minus infinity to plus infinity, and you get a new function called f hat. In this case, it actually kind of looks like this. You could do the math, and it comes out to be 1 over 1 plus k squared. But the nice thing about this Fourier transform is that you can go back. So there's an inverse, which essentially is just flipping the sign and doing the same thing over again. Some calculations, so if you were doing the frequency analysis, k becomes the frequency. And you could now say, well, if I want to cut out the high frequencies, I just set these ones to 0. So I take this function that I got out, I cut off everything beyond 2, say, and then I do a transform back, and I get a signal that has been passed through a low pass filter. There's many more applications of the Fourier transform. You can use it to solve partial differential equations by doing something that is essentially a spectral decomposition. There are a lot of applications here, but let's just stick to the technique here rather than the applications for now, and in the interest of time as well. So the point is that you can go back. You don't lose any information by making this transformation. It's just a different, let's say, a different representation of exactly the same signal. So you have one signal, it looks different, but it has the same information because I can go back and forth without loss, right? So that is nice in a mathematical sense, but these are continuous curves. They have a value on every x value, And although I plotted it at a finite range, they really are defined from minus infinity to plus infinity. So those are two infinities that computers do not like and that do not occur in data. You rarely have data time series that are from minus infinity to plus infinity, like forever on both sides, nor do you have data points that are valid on any time point. So that doesn't happen. We'll have discrete ones, right? But it is I'm going to sort of skip over this. So what we are going to deal with are discrete sets, discrete points. So we can imagine that as being a set of points at a sample interval of another function. We don't have to. In fact, once we're done, we don't think about it that way, but think about it in this context for now, that I'm going to take samples of x at equally spaced points. So the actual values of x are j times delta x, and compute the function f there, and that is my fj. So I have samples fj at points xi, xj. Now I can transform to n other values by doing a discrete Fourier transform, which looks a little like the actual Fourier transform. So I've got my my complex factor here again. And by the way, for those of you that aren't used much to complex numbers, you can one-to-one write this also in terms of a sine and a cosine transform without needing complex numbers, but it is all a lot simpler if you just use complex numbers. So that sounds funny, but it is. Okay, so here's our vector again. We have our incoming data, let's say the fj's, and we, rather than integrating from infinity, minus infinity to plus infinity, we just sum over all of the data points we have. Since we sum over all of them, the dependency that is left is just on k, and so we can do that for any k. But we're not going to do that just for any k. We're going to do that for k, also ranging from 0 to n minus 1. So that seems a little bit strange, perhaps, and we'll see what the outcome is. But it is another transform. It is a variant of Fourier transforms, and you can back transform it by doing the exact same thing, but with the opposite sign. And then it turns out if you do this to make everything work such that the back transform of the transform is the function itself or the data itself, you have to divide by 1 over n. One could make this symmetrical by having both of them dividing by square root of n. In numerical applications, nobody does that because you do not need that square root for anything else. So it's just a superfluous square root there that is for no reason. But that means that either in the first or the second, we need this vector of 1 over n. Now, a few things are happening here because we've written, if you look at the back transform, this is a signal fj that is periodic because these are periodic functions. In fact, there's a bunch of relationships here, and one of the things that you could see is that if you took this literally and you didn't restrict your k to 0 to n minus 1, but you allowed negative k values, so those would be negative frequencies or waves moving in the opposite direction, you could actually just show with a little algebra that f minus k is the same as f at n minus k. So the point n minus k is actually, those are the negative frequencies. So you've got some positive frequencies, and then up to about k equals n over 2, the rest you could interpret as as negative frequencies. But it's an interpretation because on a finite grid, there's actually no difference in the signal of a negative frequency or a n minus k frequency. So you're going, in a sense, so fast forward that it seems like you're going backwards. If you've ever seen movies of wheel spokes, of something that's going fairly fast, but it seems to go backwards, you're basically seeing this effect of aliasing, where a negative frequency is equivalent, is purely equivalent to a positive one. In fact, you could add any number of values of n to your frequency, and it would still be the same signal. So you can't distinguish those signals. It also means that if this is a true sampling of something, there's a highest frequency that you could resolve at this given level of point, which is n over 2. in these units. These are sort of integer units. There's ways to transform that into a sort of physical units. But so there's the highest frequency you could fit, and it's n/2, and it's called the Nyquist frequency. So anything higher than that, you would likely interpret as a negative frequency. So going the opposite way, and so there's a limit there. Okay, so let's look at this formula once more. We have a phase vector, a complex phase vector, multiplying f. But we can also see this as a matrix vector multiplication, where fj is the vector, and this is the matrix with elements with row elements j and column elements k. So this could be seen as a matrix. Let's call it mjk, and then all we have here is a matrix vector multiplication. So we'd say, well, let's use our linear algebra again. Let's fill a matrix with these values and just use a blast routine to do matrix vector multiplication, and that must be very good, right? And while as a matrix vector multiplication it's good, it still takes of the order of n² operations to do this, and that turns out to be much slower than you need it to be. So there's a lot of structure in the values of this matrix, if you think of it as a matrix, that actually allow you to do better than this n² algorithm. So just for comparison, if you were to implement your own slow Fourier transform, discrete Fourier transform, this is one way you could do it. So suppose I have a vector of f values coming in. By the way, these are all complex, and we're going to use that. In C++, the complex values, complex types are denoted, they come from the complex header, and they're also denoted as std : complex, and then the underlying floating point of the two parts, the real part and the imaginary part. And that's a bit much to write, especially if I'm going to then embed it into yet other template things. So it's quite common to have a type def where I say, whenever I say complex, I mean std complex double. So complex here is another name for a double complex number. So I have two vectors here. One comes in, so that's hence the const is my input f vector. The output f vector is this f hat, and then I have a way to flag whether I want it to go forward or backward, so the inverse or the not inverse, which just changes a parameter here. And so there's just a double loop that does exchange, that computes the matrix element. So this e to the I 2 pi ik over n is right here. That's this thing, and then multiplies it by fi and has a double loop to make sure I get all of my elements. And so that's our order n², sort of our own BLAS implementation. So this is pretty much the worst thing you can do to compute Fourier transforms, but this is what it's supposed to do. So whatever happens, at least has to be equivalent to doing this particular computation. So, by the way, while Fourier was the first to say, hey, you can write any function in terms of these periodic functions, that's great, Gauss was one of the first to realize that it would be good to use on discrete sets. So he came up with discrete Fourier transforms first. And so this is well before computers were a thing. And so for Gauss, it was even more important to realize that this is a lot of computations, this order n² stuff, to do if I'm just even doing some examples. And being a smart guy, he came up with a much faster way to do it, something we now call the fast Fourier transform. And so now here's an unfortunate thing. Not that many people were doing Fourier transforms, I guess. And even Gauss thought this was just a clever trick. So he wrote it up in his diary, but he never really published it. His diary was published later. But so nobody really knew that there was a faster way to do this. And it actually had to be rediscovered by Cooley and Chucky in 1965, and that was more in the context of computers at that point. And so there's been like a good century and a half lost of where this transform was known to somebody, but even written down, but not in a published form, and so and then had to be rediscovered. So we can't really call it after Gauss. That would be a little bit much, but he did do that. That's funny. So what is the basic idea about doing this faster? And the basic idea is that you could write an n-point Fourier transform. So there's n data points. I want n-point Fourier transform as the sum of two Fourier transforms, each of which have n over 2 points. And you're going to rewrite that recursively. And so to get down to a position where you have a single point Fourier transform, and if you look carefully, a single point Fourier transform is just the identity. So the Fourier transform of a single point is its own single point again. If you do this, so there's nothing to do at the lower level of this recursion, but you have to have 2 log n levels of recursion. But each level, you still have to combine all of the results in the end, which is about n computations, so n sums. So that means that the total order of this algorithm is of the order of n times log n, which is a lot faster than n squared. Just try it for a few values of n. Even with a prefactor that is say about 10 times larger, you very quickly for substantial sets of data win in terms of speed over the naive method. Now we're dividing this by 2, and that is nice. We could also have divided it by 3. So take 3 parts and do it recursively, and we would need 3 to the log n. But although it's possible and it might fit the data in some cases better, it is a bit annoying. And so what people tend to do, rather than creating functions that do fast Fourier transforms for sets of n that are multiples of 3, is to not do that. They will take their sample data and they will pad it with zeros until it is a power of 2 length long, and then they can just pass it to a generic what is called radix2 Fourier transform. Here's the algebra of how this is done. I think I'm going to skip that, but you could see why you could split it in 2 parts and why those 2 parts are again Fourier transforms. It is complex in multiple ways to do this, so you're not going to do it yourself. You're going to use a function that does it for you, and the function that you're going to use it comes from a library, and there's several ones there. The most common open source one is FFTW. That stands for fastest Fourier transform in the West, or at least it used to. Now it stands for faster Fourier transform in the West because it's faster than the naive method. But a lot of the math libraries that vendors of chips bring out, like the Intel MKL library or the IBM ESSL, have their own versions, which are often faster on their own architecture. And in fact, I think you can get the Intel math kernel library now for free, and so you could use that too. It works a little bit different in the interface, but does offer fast Fourier transforms. So here's an example of doing Fourier transform using FFTW. So libraries have versions. This is the third major version of the library. That's the one you want to use if you write new code. There is still old code out there that uses the second version, and then you'll have to learn that one. But let's just look at the third version, which is the current one. Same complex thing. And so rather than having, so I wrote the same interface, but there's a few things that are funny about fast Fourier transforms, and pretty much all the libraries follow this, is that you create a plan first to do something. So there's many ways you could optimize this, and to know how to optimize this computation, it helps for the FFT implementation to know what the size of your data is, how it's laid out in memory, etc. So you create a plan based on the number of points and where the data lives, but that doesn't do it yet. That is just a plan, and then you execute the plan, and then afterwards you can destroy the plan. FFTW is a C library, so you'll again get this idea of where you have to pass the pointer to the first element. So that's our f.data here. It's even a little bit more annoying in that it wants this pointer to be of the FFTW underscore complex star type, which is entirely compatible with the complex numbers in C++. But because it's a C routine, it doesn't know that, and so we'll have to tell it this f data thing points to a complex number of this type, which is just the same as if it was an FFTW complex star. So that's why the fast is. Fast, we can go forwards and backwards. And then there's an extra parameter that's nice in these plans, is that you can either estimate what the fastest way is to do things, or you could measure it. But measuring actually means it starts doing a few Fourier transforms for you to check how fast things really are. And that is useful only if you're going to execute the same plan several times, because otherwise it's wasted time, mostly. The inverse, just a little hint here. Remember our factor of 1 over n that we had? Most libraries don't do 1 over n here. So they say they do the inverse, but in fact they do the inverse times n. So they don't bother dividing by n. So you have to do that for them. So when you do an inverse and you call FFTW, you have to divide by n to get the actual inverse. Bit strange, just true. Okay, so we can do Fourier transforms now. I'm going to go through an example because it's important to know a few funny things that happen with discrete Fourier transforms in particular. So we're going to take an input signal. The input signal is the sinc function. Should have had a plot here, but it's kind of wiggly and it goes down towards the end. Wiggle. With about 16,000 points, I made this a power of 2. In the interval for x values between -30 and 30, we'll go do the Fourier transform, discrete transform. We'll write it out and we will plot it to see how it looks. Then we will then we'll do the inverse. Oh no, and then we're going to actually check if it's true. Sorry. So the idea is this is our function. This function is known to have a Fourier transform that is what is called the rectangle function. The rectangle function is 0 outside of k -1 and 1, and inside k from -1 to 1, it's equal to 1/2. So we want to know if that's true. When we take samples of this function of 16,384 and we pass it through the Fourier transform, is it correct? This would be, say, our unit test of the Fourier transform. So here's our code, creating my f and f hats with n numbers and elements, filling the values. I don't really need the x values here, so the x scales are going to be unknown, just numbers, integers from 0 to 16,384. But I do need to compute the x values and then compute sine x over x, which is the sinc function. And I just make sure that if x is 0, I take the appropriate limit value instead of infinity or 0 divided by 0. So that gives me my signal f. I create a plan to fast Fourier transform f to f hat. I execute the plan, destroy the plan, and write out the results. So write out the fi's data and the f hat data. And then let's plot them. So here, I don't know if you, oh yes. So on the teach cluster, if you want to do that, I'm going to plot using Python. So I chose to use the Anaconda module for that, only for the plotting with Python, not for the code. The code just needs GCC and FFTW. I'm compiling the code, then I'm linking it. The link command has -l FFTW3 as the library name, but other than that, it works. I'm writing out the output to a file. And then I'm going to use IPython to print as a plot thing. Doesn't really matter how plotted, but I'm going to plot the f values first. So this is the sinc function right here. If I had kept the x values, this would be centered around 0, but I did not. These are just samples numbered from 0 to 16,384. And then you would expect, because the continuous case has a rectangle function as the Fourier transform of this, that if I plot the second column, which is the f hat, that I would get that. But what I actually get is this. So that's a bit surprising, maybe at first. I get what could maybe be called an h function, because it looks like an h, rather than a rectangle function. But this looks altogether wrong. Like, that had nothing to do with the rectangle function, does it? And so that's that. So let's resolve that mystery and see why this is actually exactly correct. So the first thing we're going to do is to notice that this signal that we get is located near zero and near the end, but near the end is really an alias for negative values. So what we're going to do is we're going to take these, reinterpret them as negative x values and paste them on the other side. So that's what this little Python code does. And then we zoom in to take just 30 points, I think, on each side. So there's 30 points here and 30 points there. And then we do see some sort of more sensible signal. So everything outside of this is pretty much zero. Up to about 0.20 here, it starts oscillating like a maniac. And then after 40, it dies down again. Okay. So the reason that this is around 30 is because I took 30 points, right? This is not something inherent. I chose 30 points. So this is really the positive side, and this is the negative side. So this is closer to a rectangle function in that the outline here is sort of a rectangle function, or the square of it is a rectangle function. The amplitude is already correct. But I still have this odd oscillation going on, and it seems like there must still be a bug in the code, and there really isn't a bug in the code. This is correct. But that has to do with the fact that we're shifting the interval. So the true interval goes from a negative value to a positive value, -30 to +30. But the way we've sampled things, our first number is called 0, and our last index is 16,384, which means that it isn't centered around 0. It's shifted by 8,000 something, and that causes a phase shift. And this phase shift is actually the most oscillatory function that fits on the interval. So what you really see is that these values are all correct in terms of what we expect, except these guys have the wrong sign. So they flip sign every other time. So let's undo the flip sign by actually multiplying alternatively with 1 and -1. And this is not a Python lecture, so I won't explain why this works. But if we do alternatingly multiply every signal by -1 and 1, we get to good approximation the rectangle function. Yay! So this is correct, but this will happen, and in fact, in most applications, you will not have to undo all these things. You can handle the Fourier transform as it is with all its extra oscillations and its shifts, because you actually will not care that that's happening. But it is, if you ever wanted to check that a signal is what you expect it to be in the continuous case, then for comparison with the continuous case, you would have to undo these things. So a few notes, and I think we'll wrap it up here. Is when you're using the Fourier transform libraries, you create a plan. It contains all the information to compute the transform. It needs pointers to the input and output arrays. It's a C. There's typically C libraries or written in C. So that's why. You can reuse plans in your program. So if you have to do a lot of Fourier transforms on the same vector, make the plan once and then execute it many times instead of creating a plan, executing it, destroying the plan, create a new plan. You don't have to if it's working on the same array with just different values. If you're doing that a lot, you could switch from FFTW estimate to measure, which will actually measure what the fastest way is to do things. All the routines so far have worked with double precisions by default. It is possible to use single precision as well, but you might have to link a little bit differently. The remainder of the slides were mostly about how to do multidimensional Fourier transforms, which you could read up on if you want, and some hints on how to exploit symmetries in your data. But I think we will stop here. This will be enough. Yeah. So any questions on this that I could answer at the moment? Okay, well, for those of you that stuck around for the extra 50 minutes, thank you. There is an assignment. I think it's posted already, but Because the current assignment isn't due until tomorrow night, this next assignment, which will use the Fourier transforms, also is due a week from tomorrow. So although it's posted, and so if you are done with your current assignment, you could start look at it. That's okay. We do not expect you to. We don't want to crunch this assignment into 6 months, especially because it's a really nice assignment. Let's look at it for a second. Yes, it's going to look bigger than oh, it looks big. So I have to share my browser window. This one? Yeah, looks like it. Okay, so it's going to be about gravitational waves, the phenomenon that, or the detection of which led to a Nobel Prize in 2017, so fairly recently. And what we're going to look at is actually we're going to mimic how they analyze data coming from the LIGO observatory. So the signals come out from that. They're time signals of presumably the gravitational wave passing through that detector. And then there's predictions on what that signal should look like that come from simulations. Simulations of, say, colliding or merging black holes. And they give a very particular signal. And so we can see if the signal that is predicted fits with what's seen in the detector. And that's how we know that it was, say, a binary black hole merging into a single black hole, or whether it was a neutron star merging with a black hole or two neutron stars, which are actually a little bit more tricky, but you can ask Marcelo all about it because he's the expert on this, not me. But the point here is that we get some signals out of a detector, and we have prediction signals, and we want to know if any of the signals we got out of the detectors are in fact predicted gravitational waves. And we say, hey, we have a gravitational wave. So it does that in more or less in Fourier space, or in a waveform analysis. And so the oversimplified way that this is done is that there's a set of predicted waveforms, so time series if you want, from the simulations. And then we have measured signals, and then we perform a power spectrum analysis to see if they have similar power spectra than, say, gravitational waves. And if they do, then that's a hit. Okay. The reason you do this in the Fourier domain is that it's much easier to see that they are the same. You don't really know exactly when the signal starts until you start measuring it. So a small shift in how you timed your measurement could cause a big change in whether this is matched or not. Whereas if you look at frequencies, the frequencies in that signal that is shifted actually do not change much. So it is a much more robust thing to do this in the Fourier domain. So rather than taking those exact time domain signals, you Fourier transforms them, and then you see if they overlap substantially. So we call those overlaps correlation coefficients. So we really see if one signal correlates highly with a predicted signal. So we're going to do pretty much a similar thing. You'll get some data in this directory. The data is there's 32 detection signals. By the way, this is pretty much all fake. This data, the prediction data is based on an actual simulation. So the generic shape is correct. But none of the detected signals are actually coming from LIGO. We made them up so that we know that some of them will match our prediction and make this assignment doable, rather than having by accident a set of detections that do not have gravitational waves, which would make for a rather frustrating or boring assignment. So you've got those 32, and you're going to do and you should read it through to see what it actually does. But you're going to take the Fourier transform, the Fourier transform of each of the signals, prediction, and the 32 measured ones, and compute the power spectrum, which is essentially the square of of the Fourier transform. So that is nice in the sense that from then on, you only have to worry about real numbers, whereas f hat itself is a complex number. And then we're going to define the correlation between two power spectrums, f and g. One is going to be detection, and the other is going to be the prediction. And here's the definition, where these angular brackets are an inner product, which really means multiply all of the elements, element-wise, of the two signals together and sum them over all of the elements. So that's an inner product, and this is your definition. By definition, f with itself, so the correlation of f with itself is 1. That's why the normalization is here. But if f and g are very close together, they will also be close to 1. So we can have our signals, Fourier transform, power spectrum, correlate them with the prediction, and see which ones are close to 1, and then find the 5 most likely candidates for being a binary black hole merger. So you're going to need a fast Fourier transform, so you have to use UofTW. This last point is no longer true. You don't need the BLAST implementation. You can use BLAST for, say, this sum. You do not have to. But other than that, this is the assignment. So you're going to hunt some gravitational waves. Any questions? And obviously, we'll have the office hours for more questions on Monday and on Wednesday.